Uh, okay, hi everyone. So I see that there's only 6 people in the meeting, so we'll wait for a few more minutes in case anyone else is on their way to join. In the meantime, I just wanted to say that I had also mailed NPTEL. I didn't get any response regarding your assignment issue. But I think in the last class itself, someone said that the team has contacted and said that it will be resolved. So I'm sure that they will also be looking into it. But I have also brought it to their notice. Anyway, we will wait for a few more minutes and then we will start the class. Like is mute. Yeah, I'll wait for 2 more minutes in case more people are joining. In the meantime, yeah, if there's any doubts, you can put it in the chat. Otherwise, we can start the class. Okay, I think we can start the class. Uh, Hi everyone. So welcome back to one of the final few sessions of this, problem solving of this course. One sec, I was just checking. There's no one in the lobby. Okay. Uh, yeah. So yes. As I was saying, welcome back to. So this is week 7 of our 8-week course on nuclear astrophysics. And this is the problem solving session where we look at problems that can help you to solve your assignment problems. And, we do practice them together during this live interaction session. So yeah, my name is Zenia. I am a PhD student at IISc. I work in compact star physics and I've spoken about my work in one of the previous videos. And so today we are going to do something slightly different because this, as you know, in this final 2 weeks of the course, you have kind of changed, your your course of study a little bit, right? So just to recap, so far in this course, we have seen a lot of things. We started off with looking at astrophysical processes and why it's important to look at nuclear physics from astrophysical sources in the first place. So we saw that the universe is actually, rich, full of rich nuclear activity, from when stars are living to when they are dying, everything is governed by the nuclear physics and the nuclear reactions that are happening in the star. And then to formalize that astrophysical sort of discoveries, we looked at more in-depth nuclear physics. We saw how to model nucleons and nuclear particles. We saw how different kinds of models are constructed to kind of look at how stable a nucleus is. We also looked at various things related to nuclear reaction. So, for example, the cross section, which is a very important discriminant of whether or not a reaction is feasible to happen. So, yeah, so we were able to look at nuclear physics and astrophysics, uh, but still we don't have a complete picture because we are still not looking at the experimental side of things. So we spoke about a little bit of observational astronomy, but when I say experimental side of things, I really mean the experimental nuclear physics. I mean, we talked about all the theoretical stuff like shell model and liquid drop model and spin resonance parity, all that. But an important question which seems unanswered is that how are these things actually measured that we know that our theoretical models are right. So for this we need to understand the devices and the sort of experimental setups that people have for looking at nuclear physics in a experimental in a lab setting. So the point is that now we are going to go from the astrophysical world of nuclear physics to back to laboratory nuclear physics. But of course, as I keep saying, everything in the course is connected. So whatever nuclear properties we measure here are the same properties that nucleons in space have. So those are that's the kind of, and if we understand a reaction in the lab, then only can we extrapolate and understand the reaction in the extreme conditions which are there in the universe. So today we are going to look at what and all you studied in your 7th week lecture. So you looked at charged particles, neutron beams, accelerators, targets. Yeah, basically various ways of simulating, or not even simulating, performing nuclear physics experiments in the lab. So we'll start with accelerators, and I think this is something that most of you know. So essentially, this is the simplest way in which you can accelerate a particle, right? This is called a linear accelerator. As you can see, there is a power source, and you can see that the particles are accelerated based on their charges. And basically, we have applied an electric field and through a power source, and that leads to the because of the voltage difference between the tubes, we see that the particle gets accelerated because a force is acting on it. The electric force acting on the particle leads to an acceleration. You all know F is equal to ma kind of thing. So this is a very simple idea and it is a very powerful idea, but the problem is that there is a certain limit, right? So you can imagine that the volt, we cannot apply so high a voltage all the time, right? So either we have to apply a high voltage or we have to make it a very long system. So it's not practical for us to have kilometers and kilometers of linear acceleration, and it is really not feasible, right? If I want to increase my powerfulness of my machine, I have to then build an extra section of it, which is not really feasible. So because of all this reason, people started looking for different configuration of how an accelerator can be. And they said instead of linearly accelerating, which proves to be difficult, because if I want the particle, basically the more the particle is moving through the tube, the more force is felt, accelerated it gets, right? So instead of moving it in a straight line, what if we move it in a circle? And that is exactly what is seen here in the, one second, yeah, in a cyclotron. So a cyclotron is a very is basically a linear accelerator, but you kind of bend it. And the important thing is to ensure. So how do we ensure that the particle goes here and then it goes around, right? So the important thing is, as you can see in the figure, the polarity of the magnetic electric field is given in two different ways, so that as it is actually timed so that the frequency at which the particle passes is timed with the polarity. So because of the positive to negative and negative to positive, the particle is always accelerated, and as a result it always moves from uh, in the semicircle. Sorry, is there some question or something? Hello? Is there a question? Please unmute if there's a question. Okay, I think if you're not having a question, please mute your mic. Yeah, okay. Okay, so as I was saying, the cyclotron is basically a device where, people looked at the sort of the shortcomings of the linear accelerator or the LINAC, and they found a system which is easily extendable, in the sense of they said that we can, okay, instead of that, we can go to the cyclic motion. So I think you all know, but just for a revision, basically this is how you measure the frequency inside a cyclotron. And you can see here that the energy of the particles depends basically on the strength of the magnetic field which is applied, and the magnetic field is leading to electric acceleration between the magnetic regions. So basically that's the point. And the diameter. So we see that the centripetal force is required, because whenever you have a circular motion, you always have a centripetal force. You need something that is anchoring that circular motion. And centripetal force by itself is not a force, right? It has to be supplied by some other force. And here the centripetal force is supplied by the Lorentz force. So when you move something in a circle, like when Earth is moving around the sun, its centripetal acceleration is supplied by the gravitational pull. Similarly, can you please mute if someone is talking? Please mute if anyone is unmuted. Okay, I'm just going to mute you. In case you have a question, please unmute yourself. It's kind of distracting, that's why. Okay, I'm sorry, but like if you have a question, please unmute yourself. But if you don't have a question, please keep your mic muted. So, right. So this is basically the centripetal force, which you should be familiar with from your high school, mv squared by r. And of course, here we have the magnetic field, which is actually accelerating the particles round and round. So we have qvb. And of course, as I said, it is actually the centripetal force is actually being provided by the Lorentz force. So that's why we have to, we know that these should be balancing each other. And from that, we can actually find what is the velocity as a function of the magnetic field and the radius applied. So the energy is, of course, just mv squared by 2, and that's what's shown here. And frequency you can find by actually finding the orbit of one such oscillation, and you can see that the frequency is actually independent of the radius. So this is basically about the cyclotron. And essentially this is what is used. This principle of moving particles in circles is used even at the highest level. So if you see pictures of the large hadron collider, that is where they discovered, for example, the Higgs boson. You will see that it is in a circular formation, essentially at CERN. So essentially they take two protons and they collide them together at very high energies. And at the possibility is that at these high energies, there may be some threshold may be reached where some new particles may exist which don't exist stably in low energies. So that's how they actually found the Higgs, by looking for colliding particles and looking for signatures of any sort of particles that we don't recognize. So there are, that's of course more into the particle physics than the nuclear physics. But yeah, just saying that this simple idea of just moving from a straight line to a circle, that has wide applicability. I just wanted to say that. Okay. So, um, so this is about cyclotron. Now, a synchrotron is kind of like it is a cyclotron, but the issue with cyclotron is that the magnetic field varies in space, in the sense that it gets, higher between the Ds, and that's how it keeps going. But actually, these are all relativistic particles. So we can't just keep increasing the energy and ignoring the relativistic effects, and the relativistic effects can actually lead to some sort of correction terms, because of relativity. What happens is the particle's effective mass will be higher when it moves very fast, and that can actually, like, to accelerate a lower mass object is easier than to accelerate a higher mass object, right? So it's not that the proton itself becomes heavier, it's just that it has a relativistic motion. So it's something like to do with the energy mass equivalence. So what they do in a synchrotron is essentially they have a sort of secondary component that allows for the particle to actually. Okay, so this is like from another image. That's why there are two. But the point is that they vary the magnetic field with time so that it adapts to the particle's relativistic nature, and it is not just a constant magnetic field, but actually it varies so that the relativity effect can also be captured by the synchrotron. So these are different ways in which particles are accelerated. And as I said, this is important because we have to look at, if you want to see what particles look like at high energies and what kind of exotic particles can come up at high energies, we really need to look for accelerated particles. So, when you talk about cosmic rays and so on, that is, extremely high accelerated and high energy particles. And if you want to understand those, we cannot, of course, reach, maybe we can't reach the exact energy, but we can understand what kind of, see, as I said, at the ground state that we are at, nucleons are stable, neutrons and protons. But in a high energy environment, it may be that other particles are also stable, right? So for example, in the interiors of neutron stars, it's well known that, some other particles which are called strange particles, and they are not just called strange because of the English word strange. There is actually a quantity in particle physics called strangeness. So yeah, it is well known that these kinds of strange particles called hyperons and so on show up in the cores of neutron stars. So when we have a very high energies, what can happen is, basically you saw in your previous lectures, like, what we need for a new element or a new few molecule to show up from a reaction is we need to overcome some sort of potential barrier, right? So if you have enough energy, then we will definitely be able to overcome the potential barrier. So what happens is that at certain, if we go to higher and higher energies, more and more potential barrier can be overcome, and we can see more and more exotic particles, as they are called. So yeah, so this is about how you accelerate and look at particles in that way. Now, another thing that I wanted to touch upon, which I don't think is there in your class. So I don't know if this is, if if you, this is just to give you a flavor. So if you don't fully follow, it's fine, but just to make you aware that there are such things. So the point is that when we study in astrophysics, what are we finally studying, right? We're studying light, which is coming from these systems. And by light, I don't just mean the visible light. As we saw in the very first lecture, light in astrophysics comes across a spectrum, right? So there is your visible, but there's also radio, there's X-rays, there's radio waves, there's gamma rays, and so on. So so electromagnetic light is a spectrum, and we actually observe across that electromagnetic spectrum when we look at the radiation, right? But it is not enough for us to simply measure the radiation, right? We also need to extract some properties from that radiation. So one of the things that we extract is called a spectrum, and this I have already spoken about a little bit, which is that every element has a particular fingerprint, right, called a spectrum, which could be an absorption or emission spectrum, because every element on periodic table has its own unique frequencies that it absorbs or emits, right? So when we look at light from a galaxy and we see that certain or galaxy or any astrophysical source, and we see that certain lines are missing because they are absorbed, it might mean that they are absorbed by those elements which are present either in the source itself or between the source and us, right? So this is one of the information that we get from radiation. But other than that, one other important thing about looking at electromagnetic radiation that comes from space or from anywhere is to understand what produces it. So till now I to spoke about spectral analysis, which is after getting the light kind of trying to infer, right? But one other way in which we can look at it is to say what is the origin of the electromagnetic spectrum itself, right? How does this come about? From what interaction has this happened? And that can help us to understand more about what kind of medium we were looking at when we looked at the space. So this is basically, there are four kinds of interactions of charge particles with matter. And here charge particles, I'm mostly meaning the positive alpha particles, which by now you know are the helium nuclei, and the beta particles. So beta is another name for electrons, negatively charged beams. So you can see the charge part, and of course there are gamma rays, but gamma rays, as you know, are basically photons. They basically come from electromagnetic spectra, and they are kind of not, they interact a little differently, and that we will see shortly. So charge particles interact broadly in four ways. There's ionization, excitation, Bremsstrahlung, and Cherenkov radiation. And Bremsstrahlung and Cherenkov are mainly for electrons, whereas ionization and excitation happen for both positive and negative particles. And ionization is almost always the primary mechanism of energy loss. So I've attached a PDF also here, which kind of goes through all this in detail. I've also borrowed some slides from them so that we can understand better. So the first thing that we need to see is, as I said, interaction of charge particle is ionization and excitation, and these are both kind of the inverse process of each other. Not inverse process, they are kind of equivalent processes, in the sense that here you can see that in both cases we have an electron in an atom moving to a higher energy state. If that higher energy state is within the atom itself, then we can say that okay, there is an excitation because the energy level that it's moving in is within the atom itself. Whereas if there is no higher energy within, if the energy supplied to the electron is so high that it comes out of the system itself, then it's called an ionization. So both of these are triggered by charge particles which are exerting some force on it. And one thing is that both of these lead to the emission of characteristic X-rays. So I was telling you about this spectrum of particle, right? So how do particles emit light? I told you that every particle emits a particular kind of light, and it's called an emission spectrum. So here you can kind of understand why each particle has a unique emission spectrum, because every particle, I'm saying particle, I mean element. Every element has a unique emission spectrum, and we can understand why. It's because every element on periodic table has a unique number of electrons, right? That is how we define an element, based on the atomic number, which is basically how many electrons or how many protons it has. And because of this, the energy level configuration for each element is unique, and that means that whenever it gets excited or ionized and it releases some energy, then those ionization and excitations will be unique to that particular system. So this is how we can think about why the spectrum is unique. That's because the energy configuration of every element is unique, because each of them have a unique number of electrons. So yeah, so usually these energy levels are in X-rays, and these are called K alpha, for example, sometimes. So every element has a fingerprint in terms of its K alpha level, and that is also used to study. So when we see X-rays of particular frequency coming from some astrophysical source, then we are able to immediately associate that with a particular element. And that's a very useful tool in X-ray astronomy. So another process that is very important in astrophysics is called Bremsstrahlung. So Bremsstrahlung is basically a German or Greek. Yeah, okay, it's here. It's a German word, and it's also called breaking radiation. So essentially, Bremsstrahlung is sometimes you will see this terminology if you continue to study astrophysics, is that we'll see people will talk about free and bound free or emissions. So these ionization excitations are sort of examples of bound free kind of excitation, because you can see that one of the uh, one of the systems in this interaction is in a bound state, it's still in an atom, whereas the charged particle seems to be moving freely. Whereas in Bremsstrahlung, both of them are kind of free, and this happens when you have a medium with a lot of free electrons. So this is why it's important in astrophysics, because media like that are present, for example, in the atmospheres of stars, where everything has become ionized because of the high temperature. Then we have a lot of free electrons moving around. And what happens, free electrons and also of course positive ions, which have resulted as a which have become as a result of the electron leaving. You will get a positive ion and an electron, right? So when the electron approaches the ion, what happens is there is a deflection in its path, because of the, instead of going straight, it gets deflected. And this is because there is a attractive force between them, that's basically your Coulomb force. And this deflection leads to an acceleration, essentially, just like how we had deflection here to accelerate the particle. It's a similar philosophy. And because of acceleration, actually a photon is emitted, and that photon is what we see as the Bremsstrahlung radiation. So that's why it's called breaking radiation, because it's kind of like the electron is kind of moving in a different manner. So apart from this, one very interesting thing is Cherenkov radiation. So Cherenkov radiation is essentially when particles move faster than light. And at first thought, you will say that this is impossible because speed of light is a constant. Nothing can violate that. That's what special relativity tells me. But the important thing is that speed of light is not a constant. Speed of light in vacuum is a constant, right? So nothing can move faster than the speed of light in vacuum, which is of course a universal law, as Einstein established. It's around 3 times 10 power 8 meter per second. So that we cannot mess with. But as light travels with different speeds in different media, right? In vacuum, of course, all light travels at the same speed, whether it be visible or radio or X-ray or whatever. But if you go to a medium, then the light rays path can be affected. And this is something that you are all well aware of, right, from your school, because you have all seen this prism experiment, right, where you see white light which is coming, where all these components of the white light, all the different 7 colors of the rainbow are moving in the same velocity, the speed of light. But the moment it reaches another medium, which is glass, there is a dispersion, and the dispersion happens because the different components moves with different speed. So the point is that there is essentially there is a phenomenon called Cherenkov radiation, and that happens when there are charged particles which move faster than light in that particular medium, right? So this is just like a sonic boom. So like if you have seen these aircrafts, for example, videos of aircrafts, when they travel faster than speed of sound, then there is essentially a shock wave and you hear something called a sonic boom, because they are going even faster than the sound waves coming from it, and they kind of compress the sound in front, because sound is basically pressure modification in this medium. So similar kind of effect happens in light. And again, Cherenkov radiation is also very important in astrophysics, because this kind of when there are certain particles like for example, cosmic rays and etc., which move very fast, and this sort of characteristic radiation can help us to kind of measure what could be their exact properties in the astrophysical system. So Cherenkov radiation is one of the important ways in which there are Cherenkov detectors, for example. And yeah, it basically depends on the velocity, so you can find out how fast something was moving and all that, right? And it always emits this characteristic blue light. So this is at a particular particular kind of experiment that was there. So these are the different ways in which um, light and charged particles can interact. So you saw that there are free and bound particles interacting. There's free interaction, and there's Cherenkov interaction, which happens because of the superluminal motion inside a medium. So all of these emit their own kinds of characteristic photons and stuff like that. And like here the photons are kind of like the byproduct, right? They are not the main thing. Like the photon itself is not taking part in the interaction. The photon is produced as a result or as some byproduct, or like here for example the X-ray is emitted because the electron is moving up in energy level, or here the Bremsstrahlung photon is emitted because the electrons are accelerated or deviated away from their path. But of course photons can also interact with matter itself. Their interactions are of course different because photons by their nature do not have any charge. So for photons, as you see, there is a you can see that alpha, beta, gamma. You can see that gamma particles are the ones which have the most penetrating power, and we can measure this penetrating power in terms of the attenuation and so on, which you have already seen and which we will look at again. So there are different kinds of photon interactions, and these are the main three things. So photoelectric effect, which of course you should all be familiar with again from your school, Compton scattering, which some of you may know, and there's also this idea of pair production. So these are all interactions of photons with matter. So you can see that for low energy photons, it's actually the photoelectric effect which has the major role to play. So you can see that, we have an interacting photon, and if it emits an electron. So this is basically your ionization process, but from the point of view of the photon, right? So but here it's essentially it's not really an ionization, because there it was like a charged particle kind of giving the energy, but here it is not ionization, it's the photon which is giving the energy, and the photon actually disappears. So in ionization we saw that there is a k alpha line emitted, but here it is not necessarily there. So that is the photoelectric effect. And in fact Einstein, was the one who actually discovered or came up with the mechanism for explaining the photoelectric effect, and that is exactly what won him the Nobel Prize, not his later work on relativity, because it was a very important insight that the actual what is it called, the photo that light is not waves but is composed of quanta of matter called photons, was actually coming from this photoelectric effect. So the next way in which particles or photons interact with matter is the Compton scattering. So Compton scattering is basically an interaction between a photon and an electron, and it can be a free electron or a bound electron. Here the example is for a bound electron, and what happens is they both get scattered in different angles, and the photon, because it has given it's a stationary electron basically, it has given up some of its energy to the electron, so the wavelength changes. And as you know, for a photon the wavelength, energy, everything is related. So because it gives up some of its energy to the electron, it leaves behind with less energy, and that leads to a decrease in energy of the photon and change in the wavelength. So this is sometimes also called down scattering, because the photon keeps losing its energy. And this is an important effect that we have to keep in mind, because it might be that we get a reading, or we measure some radiation, but that might not be what it actually started off with. If it had interacted with a lot of things in between, then it would have given up its energy little by little, and that gives rise to this sort of lower energy photon which we finally observe, which is not what the energy started off with. So it's very important, with implications for all fields. Another important sort of the inverse effect is also extremely important, something called inverse Compton scattering. So I haven't included a slide here, but there it's just like you imagine, there we have a very energetic electron interacting with the photon. So here the electron is said to be low energy, almost usually considered to be stationary, and it's a photon which is transferring the energy to the electron. But suppose we had a very energetic electron, and that was there to provide its energy to the photon, in the sense that the energy transfer happened in the opposite way. Then instead of the photon's wavelength increasing because its energy was lost, the photon's energy would decrease, in the sense that it would get more energetic. So remember always that energy and wavelength are related. So when Compton scattering happens, the wavelength always increases because the energy has gone down, whereas when inverse Compton scattering happens, the energy is higher, so the wavelength goes down. And in that case, it's leads to a different kind of effect. So we don't really have many places where we see these very energetic electrons all around scattering, but on earth. But in astrophysics there are enough sources like that there is a special kind of effect which comes in the CMB, or the cosmic microwave background. That's called the Sunyaev-Zeldovich effect. So again, that is not very relevant here, so I did not include a slide on it. But it's a very interesting process, because just how Compton scattering is important, inverse Compton scattering is also important. It's just that we usually encounter Compton scattering because it's more likely that the photon will be more energetic, but it is not like Compton scattering only happens, the inverse can also happen. And finally, we have this pair production, where a photon is absorbed, and it actually produces a positron and an electron of so this is kind of the opposite of annihilation. If you know, annihilation is when two particles of the a particle and its antiparticle, so like electron and positron, they interact and produce energy. This is the opposite reaction. And for this, of course, we need a photon which is at least 1 MeV, because each of the positron and the electron have energies of 0.5 MeV, and that comes from energy conservation. And from momentum conservation, we know that they will move in opposite directions. If they come from a single photon, the momentum should be conserved, so they should move in opposite directions. So these are the three kinds of ways in which photons can interact with matter. And you can see that how they are energy dependent. So you can see photoelectric effect is dominant at low energies, Compton effect at mid energies, and you can see above 1 MeV, pair production also becomes likely. But of course, this is all material dependent, because it, and medium dependent. So in a rough sense, this is true, but it might not always be. There will be kind of shifts in this graph depending on what is the exact situation that you have set up. So the other important thing that photons that we have to keep in mind, apart from the fact that photons can get scattered, or they can get destroyed into electron positron pairs, is the fact that we have attenuation. So attenuation is essentially the process by which a photon beam goes through a material, and it gets, a part of it can get absorbed and part of it can get reflected. So you can see that attenuation coefficient, so you start off with some N0 kind of material, N0 photons, like you start off with N0 photons. When you have traveled a distance of X within some medium, you see that the number has gone down to N of X, right? So and the more you go through it, the lesser and lesser, the more the photons are absorbed, and N of X will be lower. And people have done studies and found that this is actually an exponential decay. So you can't see it here, but it actually goes to N0 e power minus mu X, and mu is something called the linear attenuation constant, and or coefficient. And this is basically again how to measure the linear attenuation coefficient. You can see that I am sending light of some intensity I0 here, and when the light passes through this sort of material and comes out, I get light of I. And you can see that we then look at all the angles of, because some of it may have reflected away, and then we can then find the relate I0 and I, and the distance X, and finally find mu. So to find the linear attenuation coefficient, it is actually very much related to what all are the different kinds of processes which are happening. So here you can see that there are three contributions, and those three contributions are exactly from the three interactions that I spoke about. So there's photoelectric effect, there's Compton effect, and there's pair production. And each of these can contribute to the attenuation coefficient, because each of, maybe, again, this is a linear coefficient, maybe it can get reflected, maybe it can get absorbed. So both of them are considered, whether it is absorbed or it is scattered away. Like scattering can happen from, for example, Compton scattering, right? So we have to consider all three effects when we talk about attenuation. So sometimes it's also useful to talk about the mass attenuation constant, and that is when you just divide by the density. And here this is useful because it removes the sort of the medium dependence in the thing. So it just tells you, one second. Yeah, it removes a sort of sensitivity to the medium so that we can just get an idea of how much is an attenuation in uh as in the different kind of it removes the sort of integrity of the material itself, and we can kind of understand what is it for a general like a species of that material. So that is why we have attenuation coefficient. So just to recap, we have now looked at, first of all, how we produce charged particles of high energies, and also how these can interact with different kinds of with matter. We also looked at how photons interact with matter, and of course these two are different because photons don't have charge and they do. So with this we can go to the question section. So before I move to questions, I wanted to say this now because I might forget it by the end of the class. So as you know, this is week 7. So next week on Monday we will have one more class, which will be your last official TA class for week 8 material. And in that class, as usual, I will go through the week 8 theory and solve some questions which are relevant to your assignment. But also, we are going to have, apart from these 8 sessions, we are going to have one extra session, which is going to be probably in that same week. I'm not sure of the date. So I have just told them that I'm willing to take another session also. So that session is going to be like a complete revision. Okay, so it is going to be 2 hours, like how we have these sessions normally. It's going to be a complete revision from week 1 to week 8. So just to say again, next week, next Monday, as usual, 6 to 8, we have the week 8 session, what we usually have. But after that, probably in the same week, I think on Wednesday or something, I had told them, we will have one more class, which is exactly for your exam purpose for recapping all the concepts. So what I would say is that I encourage you guys to mail me in advance for that session. So week 8, I will just follow whatever is in your lectures and what has been done in the assignment and kind of do that kind what we have done. But for the last class, I would say that because it's a recap, I can make it more personal. So if you guys mail me with what are the specific topics that you want emphasized on, that'll be really useful for me. Then I can prepare the revision class in a way that is useful to you also, right? So yeah, I encourage you guys to mail me for that, and anything else that you want me to cover. If you don't have any particular preference, I will just try to distribute the material and go through all the weeks. No, I'll definitely go through the entire course once, like as best I can, and emphasize the important topics. But if there's something that you particularly don't understand or you definitely need cleared before the exam, please like bring it up, and that would be the perfect session for it. And also if you have any, we can, that class also can be for problem solving and doubt solving and all. So I can keep a particular time in that class, like the last half an hour or something can be just to discuss the doubts alone. So we can kind of have it like a free class. So I have not planned anything for it yet because I wanted to get some idea from you guys, and that's why I'm telling you in advance, so that you guys can kind of mail me, and I can kind of take stock of what are the topics that many people are requesting and maybe not so clear. So this is about the extra class. And now we can go back to our usual thing, which is about the um, uh, problem solving. So yeah, as it says, please have your calculator ready. I don't know, I think you will be allowed a calculator in the exam also. So yeah, it's fine to use a calculator now. I don't know about your exam, if your exam format is given to you or not, but I'm pretty sure they should be allowing a calculator as far as I understood. So yeah, we'll do some questions relating to what we did today. So this is the first question. As usual, please put your answers in the chat. Oh, they gave the exam format. Okay, good. So then you know how to prepare. Sorry, there was a grammatical error. Yeah, please solve the question and put your answers in the chat. So in another, I guess, 2 weeks or so, you will have your exam. 2 weeks or little more than that. So make sure you know these sessions. If you have followed these sessions and you are doing the problems, it should be easier for you. I hope, because that will because you are already having practice over the last 8 weeks. So yeah, please, I don't see any answers yet. Please put the answers in the chat if you have. Okay, I see two people have answered in the chat with two different answers. Others also, please try this question. It is a direct question based on what we have done. So please try it. I see two different answers. It will, so, definitely we need more answers to see what is the majority opinion. Any other answers in the chat? I don't see any other answers in the chat. The people, I hope you're solving. Okay, I see one more answer, which is A. Now I have three different answers. Others, please give your answers also. This is a very simple question. Everybody should be able to solve it. So please put your answers in the chat. Others, are you solving, or is there anyone who does not know how to solve this question or is having difficulty? Please put that also in the chat. This is based on a very direct formula of frequency of the cyclotron. But if you don't recall it, or if you're not knowing how to do it, please, you can check your lectures also. But it's just a direct substitution of the formula. I'll give 2 more minutes in case anyone is between solving. Okay, one more person says A. Any other answers in the chat? Again, for your exam, it'll be good if you solve the questions. And right now, since you're sitting in the class, it's a good opportunity for you to, solve the questions now itself. So your practice is done. Okay, rest of you can like try it out. I'll show you the answer. The answer is actually D. So I'm a bit worried that none of you got the answer. So it is based on this formula, the frequency of the cyclotron, QB by 2 pi m. And if you substitute all the values, then you will get 11.2 megahertz. So where did you guys go wrong? Like, this is a direct substitution question. I am confused that there are so many people saying A. Is there any mistake in the solution? Because this is 4 Gauss. 4 Gauss is basically 1 Gauss. Okay, sorry. 1 Gauss is basically 10 power minus 4 Tesla. So you put that. Then your electron mass is calculation mistake in the 10 to the powers. No, I mean, I solved this and it was giving 11.2 only. Okay, are you saying you made a mistake or is the solution having some problem? Okay, fine. Yeah. So yeah, be very careful when you do the calculation. But even then, like all of these are megahertz. So all of the powers are the same, 10 power 6 only. Only this value should change, right? And that is based on Q, B, and M. So just remember these M and E, that is very going to show up everywhere. So just remember the mass of electron and the charge of the electron if you don't remember it already. And be very careful. Right now it says an electron, but if it's a helium, if it's an alpha nucleus, you have to change the charge and the mass, accordingly. And I hope you guys know how to do that. Even if it's a proton, you have to change the mass. So here's a question. Will a proton have a higher or a lower frequency when compared to this? A proton in the exact same field, will it have a higher or a lower frequency? Please put your answers. Yeah, okay. Someone says lower. Someone says higher also. Okay, one more person saying lower. Others are not listening, I guess. Okay, so the answer is that it will be a lower frequency because the mass is in the denominator. So we have an inverse dependence on mass. And as you know, a proton is more massive than an electron by like 1,000. It's roughly 2,000 times more massive than an electron, 1,800 kind of. So frequency will also be scaled by that value. So the mass is 1,800 times higher. So the frequency will be 1,800 times lower. So it will be somewhere in kilohertz, I guess. I have not calculated. I am just guessing based on what we know about the mass of the proton and the electron. An alpha particle will be even lower because alpha particles have 2 protons, right? Sorry, four. They have 4 nucleons, so it will be 4 times lower. Okay, so this is the next question. 16 O ions are accelerated in the tandem accelerator at TIFR Mumbai. And I think this was mentioned in your classes, but the tandem accelerator is a LINAC, it's a linear accelerator. The operating potential difference of the accelerator is 14 MV. MV is megavolt. How many or million volt or megavolt? Both are the same. And how much energy does a 16 ion electron, 16 oxygen ion acquire if it is in the 4 plus state? This is also a very direct question. I'll give you 5 minutes to solve. You don't even need 5 minutes actually, you just need 2 minutes, but I will give you some time to solve. I don't see any answers in the chat. Are you guys solving? Do you know? Okay. Okay, I'll give you 2 more minutes to solve the question. Okay, someone says 56 MeV. Any others who have solved? I only see one person in the chat who has answered with option A. Anyone else answering in the chat? I'll give you 1 more minute. Okay, one more person says A. Okay, someone says D. 8 trillion EV. Others, are you trying or shall I move to the answer? Think I can move to the answer. So, sorry. The answer is actually 56 MeV. I think two of them have given the correct answer. So basically it's based on your potential, because you know that there is potential energy difference they have given you, and the potential energy is given by Q into V. So this is from your basic electrostatics. The potential energy of an electric field is given by potential times the charge. And here, how do we know the charge? Because it's in 4 plus state, right? So it is 4 and then 14 times 10 power 6. And that's how we find the charge. Okay. So this is how to find the potential energy inside a that a particle is accelerated to in a linear system. Okay. Next question. A linear accelerator is designed to generate a beam of 10 GeV protons. GeV is giga electron volt. It has 5,000 accelerated tubes separated by gaps. And what should be the average voltage? So again, this is a very easy question, direct question. You can solve this even if you don't know nuclear physics. So please give. I want more people to answer. I've only seen 2 or 3 people answering till now. So I would like more people to answer this one. Yeah, okay. I see someone has said A. Please mute if you're not talking. It is, okay. If you have a doubt, you can unmute, but otherwise, please mute. Okay, someone says 20 and someone says A. Others, okay, I see B also as an option. I see all the answers almost. So others, please also answer this question. Any other answers? I'll give you 2 more minutes to try out the question. Okay, I see one more person has said A. What was that? I don't know what happened. I hope I'm still audible. I think there was some network change. Yeah, okay, okay. I see your answers. I see that you're all saying A. Okay, so the answer is A. The others, please check. So, as I said, this is such a question that even if you don't know any nuclear physics or what is accelerator, you should be able to do it. So, basically, we have 5,000 gaps, and we know that we finally need 10 gigavolts. So, the average voltage we need is just the division of both of them, right? So, that is how you have to solve this. So, it is a direct question, and it's very, yeah, again, you don't really need any nuclear physics also here. So others, I hope you might have made some mistake in the powers. So please be very careful with these things. Giga means 10 to the power of 9. Mega or million, they both are the same. That is 10 power 6. And of course, when Gauss is there, as we it seems like my network is having issues. Can anyone in the chat just confirm if you can hear me and see me? I just got a message that my network went down. Okay, okay, fine, fine. So it's fine. Okay, good. So, right. So I was saying that giga is 10 power 9, mega is 10 power 6. And when you have Gauss, 1 Gauss is 10 power minus 4 Tesla. And of course, you have to remember mass of electron and proton and all that. So proton mass is 1.6 10 power minus 27. So as I said, it's roughly 2000 times more massive than electron. And you just need those two because others are all just multiples of this charge, right? So yeah, make sure you don't make mistakes in this. Like these are easy questions. Don't make mistake based on maths or something like that. Okay, cool. So that is also done. So yeah, this is the next question, and here you can apply what I just said. A particle with charge 4 times that of an electron is moving in a cyclotron, which has this frequency. There is a magnetic field of pi by 2 Tesla and perpendicular because of course we need it to be perpendicular for the Lorentz force. Considering the particle as non-relativistic, so we don't have to think about synchrotron, just cyclotron, find out the mass of the particle. So yeah, so this is a direct question. So please, I want more people to answer this time. So please, all of you start answering. Yeah, I don't see any answers yet. People, please put your answers if you are done, say, solving. I'll give you a few more moments because you need to, yeah, this has some calculation involved. Okay, one person has said B. Any other answers? Okay, I see two people saying B, one person says A. I'll wait for 2 more minutes in case anyone is yet to answer. Okay, it seems that most people are between B and A. See, one more person has said A. Yeah, I think we have a good number of answers. The answer is actually A. Those of you who gave B, please go and check your calculation. Again, maybe some mistake in substitution because it's again direct substitution. So here you have to do Q. Your Q here, maybe this is where you have gone wrong. Q is 4 times that of electron, right? So that is mentioned. So that is why the Q should be 4 times 1.6. Should not just be 1.6. B and F are given to you, and from that you can find the mass of the particle. So is this clear to everybody? Just be careful, read the question carefully and solve it. Okay, so yeah, I hope this is clear to everyone. We'll go to the next one. Okay. Okay, so this is a question maybe that I don't know if you know how to solve. I'm not sure if this was covered in the class. So I'll give 2 minutes in case anyone wants to try to solve this, and then I'll explain the solution. So consider a collision of neutrons with hydrogen atoms to be perfectly elastic. So elastic means that after colliding, they are just moving on their own separate paths. And inelastic collision is like when you have two balls collide. Elastic collision is your billiard balls example, right? Very famous example. Inelastic is when they, merge or they transfer their energy in such a way that they are, one entity and they go. That is a very simple way of thinking of elastic versus inelastic. So in elastic collisions, we have momentum and energy conserved, and that leads to an interesting thing. And I will show you the answer, but yeah, again, I will give 2 minutes in case there is someone who wants to try to solve this. Otherwise, I can show the answer. Okay, I don't see any answers in the chat. Is anyone solving? I'll just go to the answer, because this I also like had to look up how to do it. So basically the answer is 27, and I will show you exactly how to do it. So basically what is happening here is that even though it is a elastic sort of interaction, and the total energy is conserved, there is still a transfer of energy from the neutron to the hydrogen atom, right? And that's how the neutrons are actually slowed down, right? uh, so if you do the calculation of a neutron of kinetic energy E encountering a nucleus of atomic weight A, you'll find that the average energy loss is something like this. So average means that there are many situations, right? Like either the neutron can give its full energy. The two extreme conditions are neutron can give its full energy to the atom and it comes to a halt, or the atom and neutron have some midway point, and there are so many different possibilities possible. So there is a spectrum of energy that the final two particles can take, even though the sum of the energies is the same. The energy can be divided between neutron and the nucleus in different ways. So you can see that for the neutron of kinetic energy, and this formula I encourage all of you to derive. It's not very difficult. It is based on momentum and energy conservation. And if you do that and you find the average energy loss, which energy loss is just the initial energy minus the final energy, right? If you find that for the average interaction, you find that it comes to be something like 2 by A plus 1 squared. And you can see that for hydrogen, A is equal to 1. The average energy loss has the largest value for E by 2, basically. So for hydrogen, it's basically like two identical particles, right? Because it is neutron and another proton, and you can consider them both to be the of the same mass. So it's like when two equal particles collide, it's like mostly the energy is divided by half, right? So the average energy loss is like E by 2 is the maximum. And so you can see that by on average it loses E by 2 of its energy after each collision. So basically you get half the energy after every collision. So that means after one collision, if I started off with E, after one collision I have E by 2. After two collision I have E by 2 times 1 by 2, so E by 4. Now after three collision, it's E by 2, 1 by 2, 1 by 2. So it's E by 8, right? So every time I'm going like E by 2 cube, E by 2, 4, 2 power 4, because I have to keep dividing by 2. So you can see that I've given an example. For example, after 15 collisions, the energy will be something like this. So you can see that after just 10 or 15 collisions from 5 MeV, we have gone all the way to an EV. So that is a change of 6 orders of magnitude, right? And you can see that the question was that how many interactions will it take for 5 MeV neutron to kind of cool down to a thermal energy of this much. And you know that neutron cooling, slow neutron is very important when it comes to nuclear fission and so on. So these are kinds of important things that people calculate. And you can see that for a 5 MeV to come to not even 1 MeV, you might think 1 EV, you might think a lot of collisions are needed. But if you actually do the calculation, and you can see this is how we do the calculation. Basically, I have to find N. So we have to take the log base 2 of this entire quantity, and that comes to be 27.5. Of course, we can't have 27.5 collisions. So the answer is 27. So around 27 collisions takes you to close to 0.025 EV. And the reason for that is because if you look at this formula, you can see that A in the denominator comes at square. So there's an overall dependence of A, even though A is in numerator and the denominator. In the denominator, it comes in square. So the overall dependence is kind of like an inverse dependence. You can approximate it to be 1 by A. So that means that if I have a lower A, I have more energy loss. So the process is more efficient, right? Whereas if I have a very big A, like a very heavy nucleus, then the energy loss is very small. So if I want to lose some amount of energy, if I have each collision losing very large amount of energy, that is more efficient as compared to if I have a small amount of energy, then I need many collisions to cool down. So one exercise that I can give you, which is very easy, is to just compare. hydrogen and say carbon, right? And see how much energy. So I've already given you like one example. To reduce the energy of neutrons with the fewest number of collisions, we need target nuclei with small a. So to reach this thermal equilibrium, which is around the value that they have given, right, 0.025, which is actually the thermal equilibrium at 293 Kelvin, which is room temperature. You see that hydrogen atom needs only 18 collisions, whereas carbon needs 110. So you can do this exercise for even higher element. So carbon already is there. You can try oxygen, magnesium, whatever it is. And you will see that because of this 1 by 8 dependence, it always, we need much more collisions. And because it's kind of like a logarithmic thing, right? So it is not as straightforward as carbon is 12. So it's not just 12 times, it is like a little different. So that is about this question. I hope you are all able to follow this. Is anyone having any doubt in this question? No. Okay. Okay. I see some, you're all saying no. So I hope you understand this is a practical way in which neutrons are cooled down, right? By through collisions. If they are very energetic, fast neutrons, if you want to cool them, you have to cool them through collisions. And for this, collisions will keep on taking away energy. And for this, we need to use low atomic number systems because those are more efficient at taking away energy. Okay, so here's another question which is, seems to be long, but it's actually straightforward, but it is a long question to solve. So, a control rod has solid boron carbide made with natural boron. Okay, and natural boron consists of two stable isotopes, which is boron 11 and boron 10 in some percentage. And boron carbide has a density of this. So, you want to find the total macroscopic cross section of the interaction of thermal neutrons. So, again, till now we have been talking about the microscopic cross section, and you can see that they have actually given you the values of the microscopic cross section for boron 10, boron 11, and carbon 12, which are the different quantities involved here. So your idea is to find what is the macroscopic cross section, not the microscopic cross section. So that itself tells you kind of how to solve this. So I'll give you a few minutes because this is, I know this has a little bit of calculation. So I will give you a few minutes to solve this question. Any answers in the chat so far? Okay, I see someone has given 96 as the answer. I will wait for 2 more minutes in case others are also solving. Also, before I forget, in the last class, there was a mistake in one of the questions. I think you guys pointed it out in the class itself that it was related to beryllium and these alpha particles. I had taken it, I had not understood the question, so I gave some other answer. But yeah, I checked after the class and your answer was correct. So I have whatever mistakes, if I find, I correct it in the uploaded slides. It might not be, it will not be there in the video obviously, but it will be corrected in the slides. So please always check the slides for the latest version, and that will have the latest version of whatever is there. And there have not been any major mistakes so far, only that one the difference was there, so I just wanted to put it. Okay, so I think others, if you're solving, you can just check the answer. I'm going to go to the answer. The answer is actually 84.3. So this is a little involved question and it has a lot of steps, so a lot of scope for uh, numerical errors. But the question itself is very simple. As I said, you are given a microscopic cross section, you have to convert it to a macroscopic cross section. So for that, what will you do? You will just simply multiply by how many such microscopic cross sections are there, right? They add up to the macroscopic cross section. So we have to find the number of particles which are there. Now it is not straightforward to find the number of particles. Why? Because first of all, I don't just have one species, right? I have boron carbide, which is a molecule which contains two elements. And in the boron carbide itself, the boron is formed from two isotopes, which have different cross sections and different percentage. So we have to take into account all of this when we are solving the question. So the first thing you need to know is what is the formula of boron carbide. So I will tell you, boron carbide has formula B4C. So there are four boron for every carbon, right? And each boron, of course, I mean, not each boron, I mean, the boron, of course, has this consistency where it is consisting of both boron 11 and boron 10. Okay. So, you know, the density is 2.52 gram per cc. And please follow this question because the next question is very similar. And next question I want everyone to solve. Okay. So the density is 2.52. You can see that the mass of boron is 10.8, the weighted mass for which you know, and the carbon is of course 12. So the mass of the mixture will be 4. Okay, I should have mentioned this. Give me a second. Insert. Yeah. So this is okay. So yeah, so this is important. So now based on this, I know that in boron carbide, I have four boron and one carbon. So this is basically the mass of the mixture, right? Now, if you want to find number of atoms, you already know how to find the number of atoms from the molecular mass. You have to basically scale it by Avogadro's number and because Avogadro's number gives you the number of particles, and then of course you have to consider for each of the what is it? This is basically number density per volume. So you have to measure it by the mass density. So basically mass density of the species, Avogadro's number, because that is the number of particles is there in each mole and divide by the mass of the mixture, because you want the number density, not the mass density. So you can see here that 2.52 was given to us. This is of course Avogadro's number, and this is what we just now calculated, and it comes out that there are 2.75 10 power 22 molecules of B4C plus centimeter cube. So again, I'm reiterating, they gave us the density of boron carbide already, but that was a mass density. We want number density because we are interested in macroscopic cross section, which is directly related to how many particles are there, right? It's not related to mass of particles, related to, because each microscopic cross section is basically cross section for one particle. So I need to find the cross section for n such particles, which means I need number density and not mass density. So this is basically the number of boron carbide. But of course, because I can't just multiply, I don't have the cross section of boron carbide, right? I have cross section of the total cross section for boron 10, 11 and 12 separately. So I need to find of this 2.75 molecules, 10 power 22 molecules, how many are boron 10, how many are boron 11, and how many are carbon. So first of all, I know how to find boron and carbon, right? If there are 2.75 10 power 22 molecules of boron 4, boron carbide, I know in every molecule there are 4 borons. So that means that the number of boron is just 4 times whatever is the number of molecules of B4C. And the number of carbon atoms is just the number, because for every molecule there is 1 carbon, right? So you can see that we have also found the number densities. Now, further, we need to find number density between boron 11 and boron 10. And I know that 80% of those boron is boron 11 and 20% is boron 10. So it becomes a matter of simply multiplying the number of boron atom with how much is there. So finally, we see that this is just 19% and 80% written in terms of the decimal. So you can see that finally we get the breakup of how many such molecules are there, how many atoms are there from each species. Now we have all the number information. It becomes simply a matter of multiplying microscopic cross section with the number density corresponding to each. So don't get confused by this. We only care about the total cross section. 3843 bar. And of course, you can't just multiply this barn with centimeter cube, right? We need to convert the barn to centimeters also. So barn is 10 power minus 28 centimeter, sorry, meter square. Uh, so 10 power 28 meter square is 10 power minus 24 centimeter square. So here we have a centimeter square, here we have by centimeter cube. So finally we get by centimeter, which is what is macroscopic cross section. So you can see that, see, I multiply the 10 boron cross section with the number of atoms of boron 10. The 11 boron cross section, I multiply with number of atoms of boron 11, and the carbon cross section, which number of atoms of carbon. And then finally add everything together to get this thing. So this is what I said, that it's a very simple question in the sense that I know all I need is to multiply cross section. All I need is to do sigma, I mean, sorry, summation of sigma and n, right? Sigma times n. But the problem is to find n is a little tricky, because we don't have just a simple particle. We have a compound which is consisting of 2 elements, and in one of the elements there is actually a mixture of isotopes. So we have to take care of all those things and then only solve the question. Okay, so does everyone follow this question? Is there any doubt? Please put it in the chat. This is kind of, yeah, I understand there's a lot of steps that is there in between. So please, if you have any question, please put it in the chat. Does everyone follow this question? Did you all understand? No questions. Okay, good, 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 good. Because if you understood, the next question is exactly the same. Okay, not exactly the same. It is a little different, but you again have to find numbers. So that's what I mean. So this is about aluminum bronze, which is an alloy containing 90% copper, 10% aluminum, and it has a density of 7.6 gram per cc. Here you have to find the mass attenuation coefficient for zero point 0.4 mega electron volt gamma rays given the cross sections for copper and aluminum. So again, this will take you some time. So I'm going to give you 7 minutes to solve it. So please sit down and please try to solve the question because it is very useful. And mass attenuation coefficient, I already told you how it is related to the different processes, right? So it is directly related to your cross sections. And so you have to use what you understood from the previous question in this question also. Okay, I see one answer in the chat, B. I'll give 2 more minutes in case anyone is still solving. Anyone else? I'll give 1 minute. Okay, I think we can go to the answer. So, why is it not? Huh. So the answer is B. Good for the one person who answered. Others, I hope you are also trying, but I'm just going to the answer because of lack of time. But yeah, so essentially we have to find first we have to find the cross section which is directly related to your attenuation. I mean attenuation coefficient in general. So you can see that it is simply the cross section times the number density which we have already found before, right? So you can see that the number density is found in the same way. So again, the density we have to multiply by the fraction. So here it is not so complicated because before, if you recall, we had boron itself being made of two different particles, different isotopes. But here it is just copper and aluminium, 90%, 10%. So we can just multiply by 0.9 and 0.1 and we are good. So we can see that we just multiply by, and it is not a compound, it's an alloy. So we don't have to worry about what the chemical formula is. So you can see that number of copper atoms is given and also number of aluminium. Okay, I should just mention that. Just mention. Yeah. So, right. So I was saying that number of copper atoms, number of aluminum atoms you can find individually based on the same sort of logic that I showed before. Rho times number, Avogadro number divided by mass. And once you do that, then it becomes a matter of simply adding and summing up. So you find the cross section and mass attenuation coefficient, as I explained in the previous slides, is simply that divided by the rho. And here the rho is 7.6. So we get 0.095. So I think yeah, it is just the same question as this, but asked in a different way. So make sure you're clear with how all these concepts are related. As I told you in a class a while ago, we should not study everything in isolation, but everything is actually related in this course. So attenuation, different topic, cross section, different topic. If you think like that, then we won't be able to solve questions, right? So make sure you know how these quantities are related and influence each other. Okay. So the next question is this one. This is based on your scintillators and all that, which I didn't touch upon in my revision, but you have already seen in your class, in your regular class. So this should be straightforward. Please put your answers in the chat. I'll give you few minutes if you're solving. Okay, I see someone has said C. Others? So to calculate the energy resolution, you need to calculate something called full width half maxima, which is how usually you find out how well something is resolved. So resolved as it has a meaning, right? Whether how sharp the peak is essentially, and that information is encoded in your full width half maxima. So they have given you all the question, all the quantities required. So please try to solve the question. I'll wait for a few more minutes in case anyone is still solving. Okay, I see one more person saying C. Any other answers in the chat? C or otherwise? Just monitoring the chat. I don't see any other answers so far. Yeah, one person says A. I think we can move to the answer. We are, running a little short of time. The answer is actually A. So, yeah. So others, please check where you've gone wrong. So as I said, we quantify the energy resolution by calculating the full width half maxima. So that is basically the width of the photo peak relative to the photo peak energy. So yeah, sorry, this is incomplete for some reason. I don't know why. So you can calculate this basically in two ways. One is by the channels. Channel is basically the instruments unit, right? So they have already told you that the peak is at 380 and the instruments half height channels are 365 and 396. So it becomes simply a matter of 396 minus 365 by 380, because again, as I remind you, full width half maxima is basically the width of the photo peak relative to the energy. So basically the ratio of these two. On the other hand, if you want to calculate in actual units in keV, then we can convert the half height channels to keV using the conversion factor 662 is equal to 380 channels. So can anyone tell me why this conversion factor takes this form? You can see that once we put the conversion factor, because we are essentially multiplying everything by the same factor, it comes out to be the same answer. But I still included this because it's an interesting thing. And if I hope from your lectures or something, you should be trying to telling me why 662 is 380 channels, or how I knew this. Please put your answers in the chat. Anyone? I can show you the question again if you want. From this question, I was able to identify that 380 is equal to 662 kV. So how was I able to do that? Photo peak is at 380. Yes, correct, Vivek. So basically, as you have learned in your lectures, cesium 137 has a peak at 662 keV, and in whatever units that the MCA is using, that corresponds to 380. So because of, we know the peak of cesium and we know what is the channel units, we are able to correlate both. And in that sense, we are able to find the full width half maxima. And of course, both of them give the same result. So that is expected, but I just wanted to show you both of the cases. Okay, this is the next question. Consider a source emitting gamma rays of 511 keV. Calculate the energy where you expect the backscatter peak in the pulse height spectrum. So backscatter peak. This is related to Compton scattering, which we already discussed when I in the beginning of the lecture. So yeah, you have to find the backscatter peak. You can consider the maximum backscattered peak. I don't see any answers in the chat. Anyone? I hope you are all solving. Okay, I see two people have answered 180. Any other answers? I can give one more minute if anyone is still solving. Okay, I think we can move to the answer. The answer is actually 170 keV. So very close. So actually the way that you do it is this is the energy of a Compton scattered photon. So this is basically Compton scattering. As you can see, lambda, there is a phi and theta component. And if you do the mathematics, you will find it. Again, this is a fairly simple way to calculate it is to use momentum balance. So momentum in x direction and y direction have to be conserved. So from that you can find the relation between these angles and the final and initial velocity. So sorry, final and initial wavelength of the light. And this is the expression you can find in terms of lambda. Of course, energy also has to be conserved. So we see this energy expression which comes in by doing a similar kind of consideration. So I would say that if you have not done this kind of calculation, please try to derive this formula and this formula on your own. It is very straightforward. It's based on your conservation principles. Of course, here they are talking about backscattering. So backscattering is exactly what I was talking about in the Compton scattering thing, right? That we may get some photons which are low energy, but they are not emitted by any source. They come from the high energy photons which we were observing being scattered by the electrons which are in between our medium or something like that. So usually backscattering is when called for angles greater than 100 or 120 or something. I don't remember correctly, but here we are considering the maximum backscattering at 180 degree. So if we substitute 180 here, this is going to give me 1 minus minus 1. So that is going to be 2. So this is h nu divided by 1 plus 2 h nu by mc squared. And the nice thing is that they have actually given us 511, which is exactly the same as mc squared. And here mc squared is of an electron because Compton scattering is usually considered between electron and photon. So you can see that this becomes h nu by 1 plus 2 h nu by mc squared, and here h nu and mc squared seem to have the same value. Becomes h nu by 1 plus 2, so h nu by 3, and that's how we get 170 keV. So I hope those who said 180, maybe you made some small mistake. So please check your question, but I think this is how you do it. So yeah, please check your calculations. So we can move to the last question of the day. This is a theoretical question. So please all of you answer it with the last question of the day. So please everyone answer this and we can close the session. Okay, I see two A's and one B. Any others? You don't have to calculate anything for this. So please try to answer. Okay. Okay. Okay, so with this question, I am not very sure about this question. I don't work in experimental nuclear physics theory at all. So this is all fairly new to me. The answer that is given to us is plastic scintillators. But I thought that inorganic and plastic are the same thing. So I did search it, and plastic is the one which is the most fast. So maybe I don't know if inorganic does not. I thought these two were kind of the same thing, but this is a question that was given to me. So yeah, maybe I will check this once more, but the answer that is given to us is C, which is plastic scintillators. Okay. So I also checked online. Plastic scintillators are used for fast timing measurements, but I don't know why the answer is not inorganic. That I have to check once more. But yeah, I please you also guys can check and see if there is some. I think the answer is correct, but yeah, I don't know this field, so I cannot explain it in a way that makes sense. You work in positive. Okay, fine. So then I don't know. This is the exact like question answers that were given to me. So I mean, plastic is like kind of a subset of inorganic, right? If I understand correctly. I mean, I think that both are used kind of that way. That's why. Okay, so maybe we can ask, I'll ask the team about this or something. But yeah, please check your notes or something about this particular question. I was a little doubtful. So yeah, if Vivek says that he has experience with these things, then maybe it is true. We can also check other sources. So yeah, I didn't have time to like look at the full thing, but based on my quick search, I saw that people were like writing a lot of papers with plastic and fast timing measurements. So yeah, on that note, we'll end the class for today. So I will just remind you that next week we are going to have the final class of. We're not going to have the final class. We're going to have two classes because we will have one class which is the week 8 material, and then following that on Wednesday, if I remember correctly, we're going to have a revision class. And this revision class is going to be essentially a recap of the entire course. So I'm going to keep it free in the sense that I want you guys to mail me. Please mail me or contact me throughout the week and let me know what are the topics you want stressed in the revision class. So next week on Monday, we'll have our usual class where I will cover the, week 8 material and associated assignment questions and all that. And then in the following class, we will look at this revision. So in that revision material, please let me know. It'll be really good if you guys can give some inputs as to what exactly you want covered. And that will help me to schedule that class in such a way that that 2 extra hours is useful to you and me also, right? And if you guys don't give any particular preference, I will try to cover all the weeks as to best of my ability. Okay, so yeah, we are nearing the end of the course. So yeah, all the best for the exams and all. I know there's still some time, but yeah, I hope these sessions have been useful to you, and we'll see you once more next week, twice, as I mentioned. Okay, so yeah, thanks everyone. I think we can close the session now. That scintillator question, I will just check it once more. As far as I know, plastic is an inorganic material, right? So that's why I was confused about it. Anyway, so yeah, please, thanks a lot, and see you next week.